Now there's one more important item that shows up on any fan curve. It's the do not select area defined by the surge line or stall line. Knowing this area is important. The rotating fan wheel produces a pressure difference from the inlet to the outlet. The whirling blades keep the air moving against this pressure as long as enough air enters the fan inlet. If the fan doesn't get enough air at a given speed, the air temporarily reverses direction and surges backward through the fan. This reverse flow can cause a noticeable fluctuation in both airflow and fan static pressure. All fans surge at some airflow, so to avoid it, a minimum airflow limit is established at every speed for every fan. This limit defines the do not select area to help designers select fans that won't surge. The surge limit depends on the fan type, and it can vary widely. For example, it may be 25% of wide open airflow for forward curve fans, but for vane axial fans, it may be 60% of wide open. Okay, now we know some basics about fan curves, fan laws, and system curves. They're developed using AMCA 210 and AHRI 430 test procedures and the fan laws, and they tell us how a fan works. System resistance curves tell us how a duct system works. Together, the fan curves and system curves help us predict how a given air distribution system will work. These basics apply to all systems with all types of fans. Now Dustin and John will tell us a little bit about different fan types.
Air handling units are typically available with several choices of fan types and sizes. This affords the opportunity to select a fan to best balance energy efficiency, acoustics, and cost. The most common type of fan used in an air handling unit is a centrifugal fan, in which air enters the center of the fan wheel and follows a radial path through it. A centrifugal fan may be characterized in a number of ways. The shape of the fan blades and whether the fan includes a scrolled housing are traditional ways to characterize. Other ways include whether the fan is belt or direct driven and whether single or multiple fans are used. Let's start with the shape of the fan blades. A forward curved or FC fan has blades that are curved in the direction of wheel rotation. These fans are operated at relatively low speeds and are used to deliver large volumes of air at relatively low static pressures. Due to the inherently light construction of the fan wheel, FC fans usually cost less than fans with other blade types and are typically used in smaller systems that require static pressures of about 4 inches or less. But FC fans are usually less efficient than other fan types.
The typical application range of an FC fan is between about 30 and 80% of wide open CFM. Now this doesn't mean they cannot operate outside this range, it's just the typical range. Operating below about 30% may result in unstable operation, and operating beyond 80% will typically be noisy and inefficient. The maximum static efficiency of an FC fan is between about 50 and 65%, and this occurs just to the right of the hump on the fan curve.
Because of this wide application range, and because FC fans have a less severe surge characteristic than other fan types, they are often the most forgiving choice. This makes them very popular in packaged and light commercial equipment. A backward curved or BC fan has shaped blades that are curved away from the direction of wheel rotation. A backward inclined or BI fan has flat blades that are slanted away from the direction of wheel rotation. The more rugged construction of a BC or BI fan allows them to operate at higher speeds than that of FC fans, making them suitable for higher pressure applications.
The typical application range of a BI fan is between about 40 and 85% wide open CFM. Their maximum static efficiency is between about 65 and 75%, and this occurs around 50 to 60% wide open CFM. So BC and BI fans are typically more efficient than FC fans.
Since the magnitude of surge is related to pressure, the surge characteristic exhibited by a fan of this type is usually more severe than that of an FC fan, considering BI and BC fans are typically used in higher pressure applications. A refinement of the BI fan changes the shape of the blade from a flat plate to an airfoil similar to an airplane wing. This smooth airflow across the blade surface reduces turbulence and noise within the wheel. The result is that an airfoil or AF fan is typically more efficient than the other fan types.
The typical application range of an airfoil fan is between about 50 and 85% of wide open CFM. Now this is narrower than either an FC or a BI fan because an airfoil fan typically enters surge at higher airflows. And at these higher airflows, the surge is often more severe than other fan types. But static efficiencies can be as high as 80 to 85%, usually making them the most efficient choice. As an example, let's consider a typical VAV air handling unit that has a draw-through supply fan that discharges into a straight section of duct. Operating at 13,000 CFM and a total static pressure of 3.8 inches, the forward curve fan needs to rotate about 775 RPM, and its brake horsepower is about 13. The more efficient airfoil fan operates at a higher speed, 1,320 RPM, but requires less horsepower at 11.8.
To summarize this section, forward curve fans are typically the lowest cost centrifugal fans. Because they have a wide application range and exhibit less severe surge characteristics, they are also often the most forgiving choice. This makes them very popular in packaged units and light commercial equipment where there is a tendency for less attention to be given to duct connections and layout. Airfoil fans are typically the most efficient, but because of their narrower application range and their tendency to have more severe surge characteristics, they do require more attention to avoid problems. This makes them more common in larger package rooftops and applied air handling units, where more attention is usually given to proper duct connections and layout. Airfoil fans usually run at higher speeds than FC fans, so they can be louder. But because they result in less turbulence, airfoil fans are usually quieter in the low frequency octave bands, which are the most difficult ones to attenuate. Another way to characterize a centrifugal fan is by whether it's a house fan or a plenum fan. A house fan contains a scroll or housing that directs the air leaving the fan in one direction. A plenum fan consists of a centrifugal fan wheel, typically with airfoil blades, without the surrounding housing. The fan wheel pressurizes the surrounding plenum, allowing air to discharge in multiple directions. Historically, most large fans used in HVAC systems have used a drive kit consisting of one or more belts and associated sheaves to connect the motor to the fan shaft. However, as variable speed drives have become more cost-effective and reliable, direct drive fans have become more popular, primarily with plenum fans. With a direct drive plenum fan, the fan wheel is mounted directly on the motor shaft. With no belts or sheaves and fewer bearings, direct drive fans are more reliable and require less maintenance than belt drive fans. And since there are no belt-related drive losses, direct drive plenum fans are typically more efficient, quieter, and experience less vibration than belt drive plenum fans. Because the motor is in line with the direction of airflow through the air handling unit, the motor mounted behind the fan wheel does not restrict airflow, does not stick out the side of the unit, and it does not increase unit width. However, the air handling unit may need to be slightly longer to accommodate the motor mounted behind the fan wheel. Depending on the location of the fan within the air handling unit, a plenum fan may be more or less efficient than a house fan. Let's take a look at a few example selections. A house fan is specifically designed to discharge into a long, straight section of duct that is about the same size as the fan outlet. This minimizes energy loss as velocity pressure is converted to static pressure and turbulence dissipates into laminar flow. With this discharge configuration, a housed airfoil fan will typically require less power than a plenum fan, but a plenum fan will likely have lower discharge sound